What we're moving on to now is the work and energy portion of this unit. The title that I have here, I have 20.6.1, that's incorrect. It should say 20.3.6. I just want to correct this so that I don't have this problem next time I teach this course. So this is section 20.3.6, and it's on page 22 of your unit handout. We're going to be looking at a few things that are definitions today. We're going to have to define work and define energy. Just like most things in science, most terminology in science might have a different meaning in a science or physics class than it does out in, the working world. We tend to confuse weight and mass when we're just out in the real world, but in physics there's a distinction between them. Work and energy have very specific meanings. We're going to learn that work and energy are both scalars, which means that whatever work is and whatever energy is, there's no direction associated with them. And then we're going to be doing some calculations that involve work. So we're going to start off by defining energy. And this is going to be a very weird set of definitions, because look at what the definition of energy is. Energy is the ability to do work. So when I eat my Wheaties in the morning, or I have my breakfast in the morning, or I have my lunch, when I go throughout my daily life and I eat, I'm consuming something called chemical potential energy, and it's in my system. It's stored energy within the cells of my muscles. And because I have that energy, I have the ability to do work. The less energy that I take in, the less food that I eat, the weaker I get, and the less I have the ability to do work. That's the definition of energy, and it's a very vague definition. Now let's define work, because if I'm saying energy is the ability to do work, then we have to know what work is. Well, it turns out work is a transfer of energy. And taken together, you guys, these two definitions are not very helpful, because I'm defining energy by saying it's the ability to do work, and then I'm defining work as saying, well, it's a transfer of energy, and it just appears as though I'm going around and around and around in a circle. But let me explain the significance of these two definitions. If I take energy into my body by consuming food, and the type of energy is chemical potential energy, that's the type, and it doesn't really matter what the type is, but I consume energy by putting food into my system. Then, according to the first definition, I have the ability to do work. So what happens when I do work? We haven't really described what that involves, but when I do work, let's say I'm moving some boxes from my house that I'm moving out of into a moving truck so that I can move. Well, that's work. We all know that's work. I go upstairs and I grab a box of books and I carry it downstairs, and then I put it in the truck, and I repeat this and repeat this and repeat this. I'm doing work. Well, what I'm doing is I'm transferring energy from my body to something else. I do not want to talk right now about where the energy goes in this example, but every time I take a box of books and I load it onto the truck, I transfer energy out of my body. So the idea is that I eat food to fill my body up with energy, and then as I do work throughout the day, that energy leaves my body because work is transferring that energy to something else. Maybe a more specific example that you might appreciate more is throwing a baseball. So if I throw a baseball, I'm doing work to that baseball. There's no question about it. And you can imagine that throwing a baseball doesn't seem to tire me out that much. But if I were a major league pitcher and I threw 100 pitches during the course of a game, I'm tired at the end of all that because I've done a lot of work. I've done a little bit of work to each baseball, and it accumulates. The amount of work I do accumulates. And as a result, I lose energy because I'm transferring energy to the baseball. Well, where is the energy in the baseball? It's in something called kinetic energy, which you learn about in Science 10. So I'll tell you right now that the units for both of these are joules, which is abbreviated with a capital J. So let's just say that I do, in throwing a pitch, I'm just running some numbers through my head. Oh, let's say that I do 100 joules of work in throwing a pitch from the pitcher's mound to home plate. If I do 100 joules of work to the baseball, then I've lost 100 joules of energy. I've transferred 100 joules of energy from me to the baseball. And that means the baseball has 100 joules of kinetic energy. Now there's one other thing I want to add to this, and it's that in terms of work, work is done. This is not really a definition of work, but it's telling you how you can tell when work is done. Work is done when an applied force results in a displacement of the object. And I'm just going to point out to you before we delve into the deeper meaning of this that we have two things that are required for work to be done. In other words, we have two things that are required to transfer energy from one object to another, because work is a transfer of energy. If I do work to a bowling ball, I transfer energy to the bowling ball. If I'm in Taekwondo and I do work to a board with my hand, I'm transferring energy from my hand to the board. But I want you to notice that those two things I have highlighted are vectors. And the relative directions of these are going to be very important. So energy is the ability to do work. Well, what does that mean? It means it's the ability to transfer energy from one object to another. How do we know when work is done? We know work is done if there's an applied force that results, and I'm going to underline the word results because it's not always clear that the force results in a displacement, but we have to be very aware of the fact that it must be a direct result of the force. We know that work is done when an applied force, and applied is important here, results in a displacement of the object. Does anybody have any questions about those definitions or that discussion that we just had? Well, one-sided discussion. No questions or comments? All right, it's a little confusing. There are different ways to calculate the amount of work done to an object, and there is a really, really slick way to do it, but you're not prepared for it yet today. Notice here I say when a force is applied to an object over a distance. That's that force displacement thing. It turns out that if you multiply the force that's applied by the displacement, you get the amount of work done in joules as long as the force is in the same direction or the opposite direction as the displacement. And more specifically, and this is something that comes about in a formula, but the formula is not always true. I've always had a disagreement with this formula that you're going to see. I think it's a bad idea to put it on the formula sheet. But if you remember this, then you don't have to rely on the formula. It's the product between the component of the force that's in the same direction as the displacement and the displacement. So when you multiply how far the object moves by the force acting on it in that direction, then you will get the work. Why is it such a picky thing here? Well, I'll tell you right now. I mean, I'm going to jump ahead here and show you an example. So I'm going way ahead here. This particular example, you have a 120 kilogram crate that's resting on a surface, and you apply a force of 85 newtons. But I mean, if you imagine a crate with a rope attached to it, this is a rope here. All right, you attach a rope to the crate, and you kind of hang that rope over your shoulder and you start walking. You are not applying a force to the right. You are applying a force in this direction. And in this question, it's 85 newtons in that direction. Not all of that force causes the motion. The only part of that force that causes the motion of the crate to the right is that component of it. There is a component of that force that pulls or moves the box to the right, and there's a component of that force that lifts the box a little bit against gravity. This force that I've highlighted in blue, that component, that's the component of the force that's parallel or in the same direction to the motion. So you wouldn't multiply 85 newtons by 25 newtons to get the work. I've told you work is force times displacement. You wouldn't do that. You would multiply whatever the component length of the blue vector is times 25 newtons. So that's what that means. Now, as I said, there's a formula here, but I really want you to understand that the force and displacement need to be in the same direction. I've got in brackets or opposite direction, and I don't want to address that just yet. We will in an example today. Now, it turns out that your formula sheet has decided, or the physics department at Alberta Education has decided to create a formula out of this. And this is a legitimate formula. I don't mean to say it's not a correct formula. It says that work done is force times displacement times cosine of theta. If you're going to use this formula, you need to know that theta is the angle between the applied force and the displacement. And it turns out, in the example that I was just looking at with the dynamite or the TNT, it turns out that if you were to multiply the force times the cosine of the angle, you will get the component of the force that's in the same direction, so then you multiply by the displacement. Anyway, you have this formula on your formula sheet. We'll talk in detail about the nuts and bolts of it, but if you look at what we've said here, work is the symbol W, it's measured in joules. F is the applied force, and I really have to stress applied. It's not the net force. It's the applied force. We'll talk about that in detail in a second. And D is the displacement measured in meters. So when you take newtons multiplied by meters, you get joules. And at this level, I don't think it's really that important to talk about units. I feel as though at some point before the end of the course, I'm going to have to discuss unit analysis with you. But it's not important for now. If you were to go to your formula sheet, we're in a new realm on your formula sheet. We're looking at the section on your formula sheet that is titled Momentum and Energy. And the formula that we were just talking about is, of course, here. Again, I would prefer for you just to know that work is force times displacement, but you have to be aware they have to be in the same direction. Incidentally, this is a formula for kinetic energy. We will talk about this after we get back from our well-deserved break. That's a formula for potential energy. These two formulas you learn about in Science 10, but while we're on the formula sheet here, you might as well just make a note that this is kinetic energy. This is for something called kinetic energy, which is energy that a moving object has. So if I throw that baseball towards home plate, I do work to it, I give it kinetic energy because it's moving. What does it mean to say the ball has kinetic energy? It means it has the ability to do work. So if it bonks you in the head, it can apply a force to your head over a distance, which is work. This is what we call gravitational potential energy. And you do calculations and talk about gravitational potential energy in Science 10. Your Science 10 teacher might not have been as picky about using the word gravitational. She might have said potential energy, potential energy, potential energy. But at this level, we're going to have to be more clear. It's gravitational potential energy. There's other types of potential energy. And later on, when we get back, as I said, we're going to delve into those two types of energy in more detail. Anyway, there's the formula for work and where you would find it. I have a few notes here to talk about with you before we go on and we use the formula. Force and displacement are both vectors. You can see in the formula that there are vector symbols associated with the force and the displacement. But work or energy is a scalar. There is no direction to energy. When I look at the Snickers bar that's sitting on my desk right now, there is something called chemical potential energy. And it doesn't have, by the way, if I looked up the energy content on it, it would be given in calories or kilocalories and also given in joules or kilojoules. Calories are just a different unit of energy. When I look up the energy content, it doesn't say 380 calories east. If it did, I would start to question what the company is thinking, because that's just not a valid thing to say. And for that reason, you can notice in the formula that there's no vector associated with work. Work is a scalar. This is a weird case. You multiply two vectors together and you get a scalar. The second note is the force must be the applied force. So if I take my dog Panda and I tie her to a wagon, I'm doing a bunch of landscaping. I tie her to a wagon and I fill the wagon with dirt, and her job is to pull that wagon from one side of my yard to the other side of the yard. I would never do this to my dog. But if I do, and I say how much work does Panda do, I would have to take the force that Panda applies. I don't care about the force of gravity. I don't care about the force of friction. I don't care about the normal force. I care about the force that my puppy Panda applies. In your notes it says, if I'm trying to determine the work done by a monkey that's pulling a wagon, then I have to use the force that is applied by the monkey. It's always applied. And many of you are going to stumble here in calculations with this, and you will use net when you should be using applied. And at times we're going to have to use free body diagrams to determine the applied force. One more note, I've already talked about this. Even though work is a scalar, you can get a negative amount of work. Now, before I explain what that means, I'll give you another example of something that is a scalar that can be negative. Temperature is a scalar. And temperature can be negative. Just because something is negative doesn't mean it has a direction. If you have, and we'll learn about this in detail later as well, but just to throw it out there to begin with, if you have a negative amount of work, what that means is you've removed energy from the object. So, for example, if I have a car, this is the headlight of the car, and the car is moving this way, this is the direction of the velocity, and I apply a force on the car that way, then the car will gain energy. And that would be a positive amount of work that I would be doing. If, however, I have a car, this is the headlight, and it's moving in this direction, but I apply the brakes and apply a force in the opposite direction, then I will be removing energy from the car. It goes somewhere else. We'll talk about that later. But this would be a negative amount of work. So I'm just telling you here in this note that work can be negative. And if it is negative, that means the object that is being worked on is losing energy. And the force is acting opposite to the direction it's moving. All right, so what happens to this formula, this magical formula that your formula sheet gives you? Work equals the magnitude of the applied force times the magnitude of the displacement times cosine of the angle if the angle between the two is 0 degrees. So before I do that, if I had a box on the floor and I apply a force in this direction and it moves in that direction, then the angle between those two vectors is 0. That's what we're talking about. And the fact of the matter is, I've told you that if you multiply the force times the displacement when they're in the same direction, you get the work. So apparently this is supposed to be equal to FD. I'm just going to drop the vector symbols because they're not needed. Well, what is cosine of 0 degrees? Take your calculator and figure out what cosine of 0 degrees is. Make sure you are in degree mode, by the way. And if there's anybody that's in Math 30-1, and I believe there's at least one person who is right now, you know, you could use 0 radians as well and it would work, but that's not going to work for the next example. What you discover is that cosine of 0 is 1, which means that when the force is in the same direction, you just multiply the force and the displacement magnitudes. What if the angle between them is 90 degrees? Now, I don't want you to do any calculations yet and type any answers or anything just yet. I want you to think about what this means. This means that I am holding, let's just say I am holding a book. I'm not going to draw myself here, but I'm holding this book. So you can't see me, you can't see my hand. What that means is I am applying a force in that direction. And by the way, that force that I'm applying in that direction to hold the book is the force of gravity. But that arrow that I've drawn is the applied force. Right? It does happen to be equal to the force of gravity in the opposite direction, but the force of gravity is not in the work formula. I'm drawing it in here anyway, but that's okay. So I'm holding this book right now, and I decide, you know what? I have to move the book from where I'm standing to a different place. Actually, before I do that, am I doing work to the book right now? No, I'm not. This is one of the toughest things, because if I told you that you had to stand with your physics textbook in the palm of your hand, holding it out in front of you for an hour, I don't think you could do it. I don't think anybody can. Well, I couldn't. You'd get very tired, but according to the laws of physics, you're not doing work to the book. You're doing work to your muscles because your muscles are always contracting when you're doing something like that. But you're not doing any work. Okay, so you say, well, what's required for work? Work requires a force and a displacement. So you decide to move the object this way. What I've drawn here is not a force. This is a displacement. So you've moved the book to a different location in the room. This is what we're talking about in this question, because the angle between those two forces, or those two vectors rather, is 90 degrees. That's a 90-degree angle in here. They're at 90 degrees to each other. So let's take a look at what the formula says happens. The formula is work equals the force times the displacement times the cosine of the angle. Well, the angle is 90 degrees. We can see that, so we get force times displacement times cosine of 90 degrees. And for at least the one person who knows about radians, you could do pi over 2 radians instead of 90 degrees. But what you discover is this is 0. Cosine of 90 is 0. So you end up with F times D times 0, which means the work is 0, but I already knew that because, listen very carefully to this, this applied force that I'm going to highlight, the component of that force that's in the same direction as the displacement is 0. There is no component that's horizontal. If the angle between them is not 0 or not 90, then you find the horizontal component. All right, let's take a look at some examples here. Wile E. Coyote attaches a rope to a 670 kilogram piano and lifts it straight up at a constant speed of 22 centimeters per second. And we could probably do this question without knowing that it's at a constant speed, but there's a reason why technically we need to know that. Remember, in our formula for work, work equals force times displacement. And I'm going to do right now what I'm going to do most of the time. I don't typically use the cos theta. Okay? Work equals force times displacement, but this force must be the applied force. Okay, so what do we have? We have an object. It's a piano. I'm not going to try to be creative here. It's a piano. It's attached to a rope. Wile E. Coyote secures the rope to the piano, and he or she pulls upwards. So what they are doing is they are applying a force upward. There is an applied force up. And that applied force is what needs to go here in the formula. We need to know that applied force. The height of 10.2 meters, when you think about it, is the displacement of the piano, because the piano goes up 10.2 meters. And we're asked to find the work. So what we need to know is the applied force. And I would like everybody to think about, but don't type an answer. I just want you to think about how we can find the applied force here. Or what is the applied force here? And when you think you know how you would get the applied force and why you would do what you're thinking, type yes in the message window. I'll give you a hint here. The applied force required to move it up at a constant speed, I think it's reasonable to say that applied force would be different if the piano were 570 kilograms. And it would certainly be different if it was a toy piano of mass 2 kilograms. And the last hint I will give you is the reason why we're going to do what we're going to do is because of what's highlighted in yellow. We know it's moving at a constant speed. If it's moving at a constant speed, our free body diagram says that the forces must be balanced. Man, we cannot get away from those first few physics principles on our formula sheet in this course. Physics principle 0 says that if the velocity is not changing, if it's uniform motion, motion in a straight line at a constant speed, then the forces are balanced. And what that means is that the applied force upwards must be exactly equal in magnitude to the gravitational force downward. We already learned about this. If the applied force upward were greater, then the piano would be accelerating up. If the applied force upward were less, then the piano either wouldn't move or it would be accelerating down. So in this case, this is the magnitude of the force of gravity, which means we can calculate this. This is a subscript for the g. We can calculate this by taking m times g times d. You could certainly calculate m times g over here and say, oh, well, that's what the applied force is, and then put the number in, but I prefer to do this. So we're going to take the 670 kilograms times 9.81. I prefer the units newtons per kilogram here because the piano is not experiencing that acceleration, times 10.2 meters. And again, it's a time issue. I just don't want to get into why this is going to give us joules. Let's just remember for the time being that when you calculate work, you are getting units of joules. Yeah. Okay, so what do we have? 670 kilograms times 9.81. If I were to hit enter right now, what I would be getting is the gravitational force, which happens to be equal to the applied force in this case, times 10.2. So we're getting 67041.54. Can I get a couple people to let me know if you're getting the same answer? Okay, perfect. I'll just park this here so I don't have to memorize it. The answer to the question then, I don't know, let's look at our significant figures, not that it really matters. It looks like I'm going to have 3 digits in my answer. So I might use scientific notation here. I could say work equals 6.70 times 10 to the 4 joules. Or I can recognize that this is 67,041 joules, which is 67.0 kilojoules. I do have to discuss something very briefly for those people that have either taken Chem 30 or are potentially in chemistry right now. In chemistry, the standard unit is kilojoules. In physics, it's joules. So when you do calculations from thermodynamics in chemistry 30, I think, Andrea, you took chemistry 30, all of your numbers are in kilojoules per mole. And when you do your MC delta T's, I believe you get kilojoules. Here, when you do the calculation, you get joules. Any questions with example 1? You know, if the object was accelerating, then you would have to do more work to find the applied force. If I told you, so we're creating a new question just on the fly, we're not going to actually do this question, but I told you that there was an upward acceleration of 4 meters per second squared. I don't know what Wile E. Coyote's been eating, but they've got a lot of strength. What that would mean is that the applied force upwards would be greater than the force of gravity. And you would have to say the following: F net has a magnitude equal to the applied force minus the force of gravity's magnitude. So to get the applied force, you wouldn't just use the force of gravity, you would have to take ma and add mg. All right, let's take a look at example 2. Wile E. Coyote then drags a 120 kilogram crate containing explosives. We already talked about this one, so I'm just going to cut to the chase here. This is me thinking. I'm going to go work equals force times displacement, but I have to look at the parallel component of the force. I have to look at the component of the force that's in the same direction as the displacement. So what I am doing is finding the red vector on this diagram. That's what I'm doing, because that's the component that is in the same direction as the motion. So I do a trigonometric calculation here. I take a detour, and I say, that 20 degrees, by the way, is way in here, right? This is the 20 degrees. I say that that side, the component that's parallel, is adjacent. So if I go over 85 newtons, which is the hypotenuse, this is equal to cosine of the angle. And that means that to get the parallel component, which I need, I have to take 85 times cos 20. And some of you might just say, well, why don't I just use the formula? Because the angle is not always going to be the angle between the two in the question. If I told you the angle up top, then cosine won't work. So we calculate this and see what we get. 85 cos 20. Always remember to turn your calculator on first. I'm in radians, so now I'm in degrees. I get 79.87 newtons is the parallel to the displacement component. And this is applied, right? I don't write applied all the time. 79.87. So that's the number that goes here. 79.87 newtons multiplied by 25 meters is going to give us a number of joules, about 2,000, I'm guessing. $1996, let's call it 2,000, let's call it 2.0 times 10 to the 3 joules, or 2.0 kilojoules. Now, that's me. If you want to take an alternate approach, I'm going to erase this stuff on the right, so I'll compartmentalize it and move it out of the way instead. This is just me, and it's what I prefer to do. And my preference here is based on the idea that I'm fine using the formula, but some students are not. Could you blindly use the formula and just say work equals FD cos theta? Well, you can convince yourself it'll work. I hope you see why it will work. If you take FD cos theta, it's going to work. You're going to get the same answer. But the only reason it works, and I can't stress this enough, is because the angle happens to be between the two. If the angle is not between the two, then this formula won't work. Any questions with number 2? Okay, so I'm going to redraw this a little bit bigger. This is the direction of the displacement vector. And this is the direction of the force. Okay, and this is not a right angle triangle or anything, it's just they're two different vectors. They're literally apples and oranges. This is the applied force, and this is the displacement. The angle between them was 20 degrees. And that's what I mean by the angle between them. If you were told on a question, for example, I would give you the exact same question, but I say that Wile E. Coyote attaches a rope and pulls so that the angle between the rope and the vertical is 70 degrees. If you used 70 degrees in that formula, it will not work. The angle that goes in the formula has to be the angle, if you draw both of those force displacement vectors starting in the same place, the angle has to be the angle between those lines. I didn't see who asked that question, but does that make sense? Okay. Any other questions with number 2? So just to be clear here, FD cos theta would not work here. All right, let's take a look at number 3. How much work is required to push a 10-kilogram box of nails to the top of the ramp shown if there's no friction? And I'm going to add something here. At a constant speed. Because if I want to accelerate it, it's going to require more work. So we're going to assume it's moving at a constant speed. Well, if it's moving at a constant speed, and I'm going to ask a very similar question that I asked with the piano question, you need to apply a force in this direction. That's the smartest thing to do. Could you push this way and get the box to go up? Yes, but you would be making your job more difficult. So you need to apply a force in the direction indicated by that arrow. In fact, that arrow is the applied force. My question to you, so let's write out our formula, work equals the applied force times the displacement. And by the way, the direction of this force is in the same direction that the box is going to move, so we don't have to worry about angles. My question to you is this: how can we find the applied force in this case? And again, if you get the answer, I don't want you to type the answer. What I want you to do is just let me know that you think you know how you would find the applied force in this example by typing yes in the chat window. A potential hint I could give you is that the applied force would be different if that angle of the ramp were different. When I said we don't need to worry about angles, I meant in the formula. And I would also say to you that the applied force would be different if the box of nails had more mass. I'll give you one more hint as a couple people start to say they've got it, that if that's the force required to move it at a constant speed, then I hope you understand that this black force would accelerate the object, and this force wouldn't cause the object to move. There's some minimum force that we need to apply to make it happen. We're back to physics principle 0. If we are dealing with a constant speed, then we are dealing with then we are dealing with uniform motion. And if we are dealing with uniform motion, then we are dealing with zero acceleration. And if we are dealing with zero acceleration, we are dealing with a net force equal to zero. Which means we're dealing with balanced forces. So the force that you apply must be exactly balanced by some other force. Now that other force is not friction, because you're told it's greased so there's no friction. That other force is the component of gravity that is parallel to the ramp. We can't get away from stuff we've learned previously in this course. This course, like a lot of science classes and math classes, but really more so here, is set up so that you use what you've learned before to move forward. So in this particular case, this is the component of gravity that's parallel to the ramp. And I'm going to choose to calculate that on the side here rather than doing it in one shot. This is that extra formula that you were given, which is mg sine theta, and in that theta, theta is the angle of the ramp. So we can calculate the component of gravity parallel to the ramp by taking the 10 kilograms multiplied by 9.81 newtons per kilogram multiplied by sine of 25 degrees I get confirmation that it's 41.458. Okay, so that is the component of gravity that's parallel to the ramp, 41.45885. So now we have work equals 41.4885 newtons times the displacement. Okay, wait a minute. What's the displacement? Well, the displacement would be the length of the ramp. Man, there's a lot going on in this question. This is the displacement. It's how far the box is going to move. So we had to have a little detour here. And now we need to have another little detour where we calculate the length of the ramp. But that's a pretty minor detour, really. This is just a grade 9 trigonometric calculation. We know the opposite side to the 25 and we want to find the hypotenuse. So I guess we can write that sine of 25 degrees equals the opposite side, which is 4 meters, over the hypotenuse, which is the displacement. I'll leave the units out. Looks like we're going to have to take 4 and divide by sine of 25. Which gives us 9.4648. And that's going to go in for the displacement. And when you multiply those two numbers, if you were to carry all of your decimals, do you get 392.4? Okay, so it's 392 joules. I don't really care about significant figures. It's not important today. Now, it turns out, when you take a look at the amount of work that we did here, we did a fair amount of work. It turns out that there is a shortcut we could have taken, but I can't really show you the shortcut because it would involve an entirely different concept that you haven't learned. That's fine, JV. Make sure you watch the rest of the lesson. Have a great break, JV. All right, let's move on to the next question. It's a fairly long lesson. There are a lot of examples here, but it's the only one we're doing today. So Wile E. Coyote has lifted a piano to a height of 10.2 meters. I don't know why, but he's dragging a box of dynamite across the floor, the canyon floor, and then he's pushing a box of nails to the top of a ramp, trying to catch the roadrunner. What happens to Wile E. Coyote? He's already weak, but what happens to Wile E. Coyote is he gets weaker. He loses energy. All of these tasks were transfers of energy. Wile E. Coyote did work in lifting the piano. He did work in dragging the box of dynamite, TNT. He did work in pushing the box of nails up the ramp. And all of this work that Wile E. Coyote did meant that energy was transferred out of Wile E. Coyote. In other words, Wile E. Coyote lost energy. And he's not very smart, apparently, even though he calls himself a genius, because he doesn't think the plans through well enough. If you've ever watched The Roadrunner, he doesn't think things through well enough. He spends all of his energy getting weaker and weaker and weaker, and his goal is to catch the Roadrunner, which to him is food, and he wants the food so that he can get energy. Anyway, I hope this analogy kind of brings it home in terms of work and energy. So you look at number 5. Rocky is driving a 1,250 kilogram car traveling at 95 kilometers per hour. There's Rocky standing on the right. And a moose runs out of the ditch into the road. The moose is Bullwinkle. When the vehicle comes to a stop, because Rocky sees his friend Bullwinkle, he doesn't want to hit him, so he slams on the brakes. Luckily, nobody is hurt. The length of the skid marks is 82 meters. Determine the work done to the car, and then we'll get to the rest of the question in a second. So let's start off with our formula for work. Our formula for work is applied force times distance. Now, what is the applied force? Well, let's draw a little picture here. I'm not going to be very creative. I'm certainly not going to attempt to draw Rocky or Bullwinkle. We have a car. Here's the headlight. The car is moving to your right. The car sees the moose, slams on the brakes, and stops here. So the car is no longer on the left. The car is now on the right. And the length of the skid mark is 88 meters. So by saying the length of the skid mark is 88 meters, you know how far Rocky traveled in stopping. You know the displacement. 85 meters. We can even put that up here. Now, this is subtle. This next part is tricky. Thank you. This next part is tricky. What is the applied force? And you can't answer that with a number just yet. We're going to have to calculate the number. But when Wile E. Coyote was lifting the piano, the applied force was the force of gravity. When Wile E. Coyote was pulling the box of dynamite, the applied force was the parallel component, parallel to the displacement of the applied force. When Rocky was, or when, not Rocky, when Wile E. Coyote was pushing the box of nails up the ramp, the applied force was the parallel component of gravity. What is the applied force here? Yeah, it is the force of friction. The applied force is the force of friction. I mean, as the car is coming to a stop, there is a normal force, there is a force of gravity, and there is a force of friction. And when you add those three forces together, you get the force of friction. But you know what? That doesn't really help us. But yeah, that's true. And that's the answer I was looking for. But we can't calculate the force of friction. The applied force is the force of friction. That's true. I don't even need absolute value signs. They're the same. But the force of friction is mu mg, and I don't have mu. So how can we find the force of friction? What's the force of friction equal to? What's the net force? In this example, the force of friction can be called the applied force, or the force of friction can be called the force of friction, or the force of friction can be called the net force. They're all the same thing. When I draw my free body diagram on the car, I've got a normal force, I've got a force of gravity, and I have a force of friction backwards. If I add those three forces together, I get the net force. But if I add them together, what I'm left with is the force of friction. And if I add them together, whatever I'm left with is the applied force. So what we can do in this case is use MA. Not always. This is the toughest thing about this lesson, is knowing how to find the applied force. Again, in the first example, the applied force was mg. In the second, it was a parallel component of an applied force. In the third, it was a parallel component of gravity. And now it's ma. So we have to use kinematics to find the acceleration. VI, VF is 0. We'll get to VI in a second. D is 88. And we want to find the acceleration. VI is 95 kilometers per hour, but of course you have to convert that to meters per second. We take kilometers per hour divided by 3.6 to get meters per second, so there is our initial speed. 26.38 repeating. What formula can we use to find the acceleration? We can use Vf squared equals Vi squared plus 2AD. So we'll have 0 squared equals 26.3 with an 8 repeating squared plus 2 times A times 88. So we are going to have to find A, subtract 26.38 repeating squared and divide by whatever 2 times 88 is. And if you're going to do this in one shot, without calculating 2 times 88 first, then you're going to have brackets when you divide. So I'm going to square this first. I subtract it to the other side where it becomes negative. I divide by, in brackets, 2 times 88, and I get negative 3.9566666666. I just need to know, I hope I've been going slow enough with this set of calculations. I just need to know, though, that some of you are getting the same number of meters per second squared. All right, now we're ready to go. Let's calculate the net force. The net force will be MA. I'm going to choose to leave the negative in there. I think it was 1,250. Yep. So 1,250 kilograms times negative 3.96 meters per second squared. Gives me this force. Now, when you look at your formula for work, there are no vector symbols on the force, so we're going to drop the negative when we put this number in here. We're simply going to put 4946. If you were to leave the negative in, technically in Physics 30 we would, because then you're going to get a negative amount of work, which means the car lost energy, but we won't worry about that. We have to multiply by 88. Our answer then, disregarding the negative, is this many joules, 435,000 joules. So a lot of calculations there. Take a look over the work, please, and see if you have any questions with the calculation part of this question. Now, we're asked what did the work and what energy transformation was involved. What did the work was friction, and the energy transformation was a transformation from the car having kinetic energy to heat. It turns out that whenever friction does work, you produce heat. That's why if you rub your hands together, your hands warm up. That's why if you run across the gym floor wearing shorts and fall to your knees and skid to a stop, your knees get burned. It's actual heat that's doing that. Now, just like the pushing of the box up the ramp, there's a real easy way to do this question. And I'm going to show it to you now so that it's planted in your head. So that when we learn why this works later, you will understand. I'm going to take the 95 kilometers per hour and convert it to meters per second. And I'm going to calculate the kinetic energy that the car has. Remember that I told you earlier, kinetic energy is 1/2 mv squared. So if I take 0.5 times the mass, and I multiply by the speed squared, I get the answer. And I don't mean I get close to the answer. I get the exact answer. And the reason is work is a transfer of energy. So if you understand that Rocky's car lost kinetic energy, then however much kinetic energy it lost, that's the work done. Okay, we have one last example to go. Any questions with any of the examples so far? The last one is really different, so it's doesn't fall into the grouping of the first 5. Any questions at all? All right, so the last one seems out of nowhere. What we have is a graph here. The graph shows the relationship between the applied force that a club face on a golf club is applying to a golf ball as a function of the distance the ball moves. Now we know the distance moves more than 4 or 5 millimeters, but that's how far it moves while it's in contact with the driver, with the golf club. And the question is, determine the work done. First of all, we can answer the second part of the question, which I'll highlight in blue, by saying the work done is a transfer of energy from being energy in the golfer to kinetic energy of the ball. The ball gets kinetic energy. Now, how do we find the work? You need to understand something, and this is true no matter what kind of graph you're dealing with in the real world. If you have a graph, and when you multiply the two variables together, if it gives you something meaningful, then the thing it gives you is represented by the area of the graph. So, for example, if we had, I'll give you a specific illustration here. If we had some kind of stock market activity happening where the dollars are changing per minute, and you plotted the graph and it looked like this, then this area equals the money. Because when you multiply dollars per minute by minutes, you get dollars. And I'm telling you that this is always true. If the product of those two variables gives you something, then that thing can be found, that quantity can be found by determining the area. And if you take a look at this question, we have force and displacement, and you know that work equals force times displacement. So the lesson learned here, rather than give it to you in notes, the lesson learned is whenever you have a force displacement graph, the area is equal to the work done. So we need to find the area enclosed by that shape. But unless you use calculus, there's no way to determine the exact area. What we do, though, is we represent the area with an approximation. If I were to draw a triangle that was here, and I don't want you to draw that, I hope you would agree that that triangle would have an area that's too small. It's missing, this triangle that I do not want you to draw is missing this and this. So what I can do now is change the location of the top of that triangle, and I might pick this. And the hope here, I might even go a little bit like this. The hope here is that this area that I'm going to shade in yellow in here and in here that we are missing is included in that. And that's a pretty good triangle. I'm going to find the area of that triangle. The area of a triangle, of course, is base times height over 2. So that would be 1/2 times the base is 5 millimeters, which is 5 times 10 to the negative 3 meters. And the height, let's see, this is 2, 3, 4, let's call it 5. And it's kilonewtons, which is 5 times 10 to the 3 newtons. So do me a favor and run that calculation through your calculator. 1/2 times 5 times 10 to the negative 3 times 5 times 10 to the positive 3, and confirm that you get 12.5 joules. Now this is just an approximation, and if you want, just memorize for a force displacement graph the areas work. We're going to use this idea in Physics 30 with other graphs. So the area gives you the quantity. This is exactly the same, by the way, everybody, as when we had a graph that had velocity and time. The area was the displacement, because velocity times time is displacement. Anyway, that's it for the lesson. Kind of a long lesson. There's a lot there. There are 12 problems. These can be very frustrating. The biggest mistake that can be made is not figuring out what the applied force is. It's not always the net force. Sometimes it is, but a lot of the time it's not. So you've got about 15 minutes left officially in class, but you know how I feel about this. Actually, what time is it? You have lots of time left, don't you? No. We start at 9. Do we start at 9? Sorry, everything is a blur. We start at 9. You still have 45 minutes left. I'm worried that it went too fast. Can you let me know too fast, too slow, or just right?